Hello, good evening everyone. Welcome to lectures of week 11. We'll discuss some of the problems today, some sample problems. Um, we'll start with, let me write down the problem first. Uh, so if Vx is equal to x square plus 3 and Vy is equal to 2y plus x for a Newtonian fluid, then sigma xy is what? So this is the question statement of the question. uh, you, give, you are given velocity along the x direction and velocity along the y direction. You have to calculate sigma xy. Now let us consider first the let us consider eta is the coefficient of viscosity. Then from lectures we have seen that sigma xy is given by this. Let us first write down the general formula. Sigma alpha beta is given by eta kappa alpha beta plus kappa beta alpha minus p delta alpha beta. So this is the general formula. So we need to calculate sigma xy. So alpha is equal to x, beta is equal to y. So the formula will be eta kxy plus kappa yx and minus p delta xy. Now the delta xy is 0. As you know that delta I is 1 and delta, let me write down this way, delta ij is equal to 1 for I is equal to j, delta ij is equal to 0 for I not equal to j. So here delta xy I not equal to j, so it will be 0. Okay, and then how to write down kappa? Kappa alpha beta is given by del v alpha del r beta. So in this case, in our case, we need kappa xy, which is del vx del ry, and kappa yx, which is del vy del rx. Now this is component of that, so it will be del y and del x. Yeah, now we know the relation in terms of x and y for vx and vy, which is given in the question. So from this, del vx del y will be 0 because vx is independent of. So let me once more write down here, vx is x square plus 3 and vy is given by 2y plus x. Okay, so from this you can calculate del Vx, this kxy, del Vx del y, this will be 0 because Vx is completely independent of y, and del Vy del x will be 1 because there is only x which will contribute to this derivative. So kyx is kappa yx is 1. So sigma xy, which is eta kappa xy plus kappa yx, and rest of the terms is 0 because sigma xy, so it will be eta into 0 plus 1, so this is eta. So for this given question, sigma xy will be equal to eta. So let me discuss once more. You are given Vx, which is x square plus 3, Vy 2y plus x. You have to find out for a Newtonian fluid what is sigma xy. Now we know this general formula, sigma alpha beta is equal to eta kappa alpha beta plus kappa beta alpha minus p delta alpha beta. Now we want to calculate for alpha is equal to x component, beta is equal to y component, sigma xy. So sigma xy, at once the delta term will go to will become 0 because delta xy is 0 because of the property of Dirac delta, this delta function, and there will be two terms kappa xy and kappa yx. Now from the definition of kappa is defined as, kappa alpha beta is defined as del v alpha del r beta. So derivative of alpha component of velocity with respect to beta component of the position. So we are calculating kxy as del vx del y, which is 0, and kyx is equal to del vy del x, which is 1. Just putting back in the original formula, we will get sigma xy is equal to eta, xy component. Okay, let us go to next problem. Number 2. Total stress acting on a material plane, total stress acting on a material plane can be obtained from now they have this multiple choice question, as you know that. So force between particles above and below the plane. B. Pressure acting on the plane. C. Force between particles on the plane, and D is none. Okay. Now, so total stress we have defined this way. Suppose we have a plane like this, Yeah. So then there will be particles above this plane, and there will be particles below this plane. We want to calculate the stress acting on this plane, but there are particles above and below the plane. Now there will be interaction between red. So this black and black, they are also interacting. This black with red also interacting. Red and red is also interacting. Now the black interaction is confined to one side of the plane. So if black are interacting, the line of interaction, so suppose this black and this black is interacting, the line of interaction that is in the one single side of the plane. So this plane is our consideration where we want to calculate the stress, but the line of interaction is not intersecting the plane. So when we are calculating the stress on the plane, the force acting on the plane, this kind of interaction force between the particles only in the single side, only the black particles, will not contribute to the stress acting on this blue plane, which is our aim to calculate. But this interaction or this interaction between red or between black, this interaction will not contribute to the stress, but because those interactions are not crossing the plane. But if I consider this interaction between red and black, these interactions are crossing the plane, and this interaction is affecting anything in this region, a point, suppose a material point is on the plane, this interaction will be felt on that material point. So the stress is force between the particles above and below the plane. It cannot be the stress is not governed by the interaction between red or black, only the interaction between red and black particles above and below. Interaction between, yeah. So when we calculated the stress, we have made two major assumptions here. That the first assumption is the particles moving through the plane do not contribute to stress. So when some particle is moving through the plane, crossing the plane, so these particles will be moving through the plane, and that is also causing some stress, but we are neglecting that part. So this is we neglect here. And the second assumption is interaction between only particles from different side will contribute to stress. So this is also an assumption, but yeah, so the as we have seen in the lecture, that the interaction between one side of the particle, as long as they are not crossing the plane, they are not generating any stress, but when they are crossing the plane of our interest, they are directly contributing to the stress. So in this question, the option A is the most appropriate option here. Okay, so total stress acting on a material plane like this blue plane can be obtained from force between particles above and below the plane. Let us move to next question. question number 3. In the case of simple shear deformation, pressure can be related to shear gamma and shear modulus G. By which of these relation? There are 4 options. So G gamma, G by gamma, C G by gamma square, D G into 1 plus gamma square. Okay, let us discuss this problem in detail now. So suppose there is this box of unit side. This side is 1, this side is 1. Now it is deformed to some other shape like this. Let's say like this shape, and the shear is gamma. Now in the process, suppose the deformation is uniform and all the points on this material is uniformly deformed. So whatever point coordinates are, they are transformed to r prime. So x, y, z, these are transformed to x prime, y prime, z prime. Now we need a relation between x prime, y prime and z prime and x and y and z. So x prime is x plus gamma into y. So the coordinate axis here is like this. So this direction is x, this is y, and this is z. So all the deformation has happened, that is in the x direction. So and y and z direction is completely unchanged. So y prime is y, z prime is z. Now if we want to write deformation gradient tensor, which is E, and it's given by this matrix EXX, EXY, EXZ, EYX, EYY, EYZ, and EZX, EZY, EZZ. Now, how it is defined? The terms of E. So E is defined like del x prime del x, del x prime del y, del x prime del z, del y prime del x, del y prime del y, del y prime del z. Del z prime del x, del z prime del y, and del z prime del z. So this is the deformation gradient tensor. Now if you write the terms, we know the relation between x prime, y prime and z prime. If I write the term, so del x prime del x will be 1. So let me write down the relations one more here. X prime is x plus gamma y prime is y, and z prime is z. So del x prime del x is 1, del x prime del y is gamma, del x prime del z is 0, del y prime del x 0, this is 1, this is 0, this 0, 0, 1. So this is the deformation gradient tensor. Now sigma alpha beta is given by G alpha mu beta mu minus P delta alpha beta. If you don't remember how we derived this formula, see lectures. This derived lecture, probably from the previous module, one lecture it is defined. Now in this case we want to find out pressure, but as you can see, the sigma alpha beta is only present if it is sigma xy. All the other sigmas are 0, so sigma xy is not 0. For anything else is sigma xx or sigma yy, anything else, everything else is 0. So if we want, but if I put alpha is equal to x and beta is equal to y, then immediately the term related to pressure will be 0. So, but we want to calculate the pressure here. So we will use the information that all the other sigmas are 0 to calculate the pressure. So we will write down what is sigma xx from this. So sigma xx, which is 0, we know that is G. This mu is dummy index, so it will run over all. So sigma exx plus exy z exz minus p, because that term is 1 is now, because alpha is equal to alpha alpha is equal to x, beta is equal to y. We are working on this. So if I take p from this to this side, this will be g. Now exx is 1 into 1 plus exy, which is gamma into gamma, plus exz, which is 0, so 0 into 0, so it will be g into 1 plus gamma square, the pressure. So if you want to calculate the non-zero term of sigma xy, sigma alpha beta, that will be sigma xy, you can calculate that. So if you calculate sigma xy from here, so this will give you g into the term, but there will be no pressure dependent term because delta xy is identically 0. So there will be some term, and that relation will give you sigma xy equal to g of gamma, g into gamma. This relation you will get if you use sigma xy, but we know that all the other sigma are 0. So sigma xx we will use to calculate the pressure. So immediately instead of this you could have used something else like sigma yy. Okay. So first we have calculated, once more recap this. So first we have calculated how the material points are changing, found out the relation between changed point and previous point. We have defined what is deformation gradient tensor, calculate each term of deformation gradient tensor, this, and from that using this relation sigma alpha beta we have calculated what is the pressure. So here this option is correct. Okay, let's move to next question. So next question is question number 5. And question number 4. In the case of uniaxial deformation, stress sigma can be related to strain epsilon and shear modulus G, as there is 4 option now. There are 4 option. A option is G epsilon, option B G by epsilon, option C G epsilon square, option D G 3G epsilon. Okay, so we'll first, so this problem, the idea is quite same as the previous one. Suppose you have one volume like this and you deform this volume in the one direction. So that's the idea of uniaxial deformation. So in one direction you have deformed this by putting some stress sigma. By putting some stress sigma you have deformed this. Your axis is like this is x, this is y, and this is z. So you have elongated the whole object in the z direction, but your volume is constant. Suppose the initial side of this object is unit, and now this has elongated in the z direction and the side has become lambda. So the volume is conserved, Even though the shape is changing, the volume is not changing, the volume is conserved. So now initial volume is initial volume is 1 cube 1. The final changed volume should be 1 again, but let us say the uh, this one z side is lambda, the other two side has to shrink because one side has become elongated, so other two side has to shrink to be keep the volume constant. So other two sides will, let's say for a moment, the other sides are e, so it is like so this side is, so something like this. So this side is lambda, this is a, this is a. So the volume should be 1, so a is 1 by root lambda. Now we want to calculate what is the deformation gradient tensor. So as you know, the deformation gradient tensor is defined as, the terms are del x prime del x, del x prime del y, del x prime del z, del y prime del x, del y prime del y, del y prime del z, last column del z prime, del x, del z prime del y, del z prime del z. Now we need a relation between x prime, y prime, z prime, and x and y and z to write down the terms of this matrix. So as the uniform, so suppose the deformation is uniform and each point has changed to r prime, so x, y and z has gone to x prime, y prime, z prime. Now x prime equal to then 1 by root over lambda x, y prime is equal to, because these two side x and y has shrinked, so y prime is equal to root over 1 by root over lambda y, but z prime has elongated size now, so z prime is simply lambda into z. So this is the relation between x prime, y prime, z prime, and the old coordinate x, y and z. Now we will use this idea uh, to complete the matrix E. So as you can see, no non-diagonal term will survive, so it will be 1 by lambda 0 0, 1 by root lambda 0 0 0 0 lambda. So this is the deformation gradient tensor. Now from this we have to calculate. Now we will use this deformation gradient tensor to calculate change in free energy. Now free energy density for deformation is given by F E half of NCKBT F E alpha beta square minus 3, where NCKBT is the shear modulus G and NC is the density of crosslinkers. So F of E can be written as half G E alpha beta square minus 3. Now there will be all the terms of alpha beta, so it will be E all total 9 terms, x y square E x z square plus y x y y y z plus E z x square z y square and z z square and minus 3. So half g. Now most of the terms are 0, only the diagonal terms will exist. So 1 by lambda plus 1 by lambda plus lambda square minus 3. So this will give half g lambda square plus 2 by lambda minus 3. So this is the free energy density for deformation. Now suppose consider in this deformed shape, consider the plane x y. So this side is 1 by root lambda, this side is by root lambda, like this, and you are giving a stress which is sigma, which is function of lambda. Now then total force acting is sigma lambda into 1 by lambda, which is the area of this small section, this area, stress into area, this is the force. Then work done to change a little bit d lambda, let's say, that will be sigma 1 by lambda d lambda, and this will be stored as free energy. So this is the change in free energy. From this, sigma is lambda into df d lambda. Now we already know what is f in terms of lambda. Previous page we have calculated. So f is half g lambda square plus 2 lambda minus 3. So from this, sigma will be half g, sigma will be lambda into half g 2 lambda minus 2 by lambda square. Half will cancel, lambda will go inside, so it will be g into lambda minus 1 by lambda square, but there will be a lambda outside, so it will be lambda square minus 1 by lambda. So this is the stress in terms of lambda. Now suppose the strain is epsilon, so lambda is 1 plus epsilon. Now in a limit for small epsilon, sigma is g into 1 plus epsilon square by minus 1 plus epsilon. Now for a small epsilon, we can write 1 plus epsilon to the power minus 1. We can expand this in a Taylor series formula and we get this. We'll keep up to power 2 and we'll use that formula here. Sigma g is equal to 1 plus sigma epsilon square 2 epsilon minus 1 plus epsilon minus epsilon square. We are keeping up to order 2, So there will be cancellation, 1 epsilon square will cancel, and this will be sigma is equal to 3 epsilon g. So this is the relation for point to be remembered here. This is the small epsilon limit. Sigma is 3 epsilon into g. Okay. So in this particular question, we were trying to calculate. So what is the relation between sigma g and epsilon? So that relation comes out to be this. So first we have taken a volume element and then considered that only one along the z axis there is a stress acting and deformation is along the z axis. So each side was unity. Now one side, the z side, is now lambda, and other two side, due to because the volume is constant, other two side has to shrink, and we have calculated what is the new x and y direction dimension, that is 1 by lambda. So because there is no distinguishing factor between x and y direction, so we can take both of them shrink equally and z direction is elongated by the applied stress. Now we have the relation between x prime and x, y prime and y, z prime and z. Using that relation, we can calculate what is the deformation gradient tensor, and we can see that non-diagonal term in the deformation gradient tensor is 0. Only diagonal terms are there, 1. So this is 1 by root over lambda. Then we have used this formula of free energy, which is derived in the earlier lectures. You can see lectures. If you don't remember this formula, this is derived in lectures. So if E is half G, this E alpha beta whole square minus 3. So we have put all the terms alpha E alpha beta. We got the relation between free energy and lambda. Then we defined how free energy is related to change in free energy is related to stress, and for using that relation we got the stress is equal to g into lambda square minus 1 by lambda. Now we put lambda is equal to 1 plus epsilon, and using the idea that we can expand 1 plus epsilon to the power minus 1 in the small epsilon limit, we got that relation sigma is equal to 3 epsilon g. So this is the desired relation. Okay. Let us discuss one more problem, which is a true false kind of problem. This problem is cross links can drive solid crosslinks can drive liquid to solid transitions. true or false type question. So obviously crosslinks can drive. So this is definitely true, because if so there are these kind of polymers, and if there are too many crosslinks, that polymer configuration is kind of frozen, because there are not much freedom to the polymer segments, because there are too much cross linkers, and it is kind of a frozen structure, and it is almost like a solid. But instead of that, if the number of crosslinks between the polymer segments is low, then the polymer segments are free to move in the solution, and the polymer looks like a liquid, because it has much higher uh, freedom to move around. The polymer segment has much higher freedom. But if the number of cross linkers are too much, then the polymer segments cannot move in the solution freely, and it appears to be a solid like structure. Okay. Again, uh, another question is, a tube model is used when is present. So this is filling the blanks type question. The options are like crosslinks, B strands, C entanglements, D metals. Now, as you can see in the lectures towards the end of this module, this week module, that if there is entanglement in the polymer structure, in the so if so this is if the polymer structures are like this, entangled, two polymers are completely entangled like this, then to study the dynamics of those polymer, we use a tube model. So tube model is something like, so in the all earlier cases when we studied whatever random walk, freely rotating chain, self-avoiding walk, or Rouse model, there we haven't considered this entanglement, but here, as we want to study the polymer dynamics, this entanglement is important here. So suppose we want to study the dynamics of this blue chain, then in the tube model we consider that a tube around the length of this chain, and polymer can only move along its contour. So after this, so this polymer after certain time can become like this, and this portion can go, so it will be elongated tube now like this. So using this, so polymer, this polymer basically rotates inside this tube, and the movement of the polymer is allowed only along its length. So using this idea, we can study the dynamics of polymer where these polymers are entangled. Because these polymers are entangled, so these polymers are like two polymers are completely, one polymer is like this, another polymer is passing through this polymer like this. So if you want to separate these two polymer, if you put a force randomly, this polymer would be, it's not allowed to cross this black polymer, so it will not move that side. So the dynamics is studied only it is moving when along its length. You can consider noodles as entangled polymer. In general, all the polymers are entangled, but up to this point we haven't considered any entanglement, just for sake of simplicity. And uh, the properties we were studying in that case, suppose radius of gyration or end-to-end distance, in those cases entanglement is not very important, but here we want to study the polymer dynamics, so there the entanglement becomes important, because the surrounding polymer, these entanglements will affect the movement of the other polymer. Okay, so that's all for this week. We'll meet for the last lecture of this semester next week. And yeah, any doubt? Okay, okay, then bye.